Hey, what up and welcome back to this new video on Thermoforge. Have you heard of the thermoplastic composites? Okay, so today I'm gonna go into the different fiber types and how do we match them with the right thermoplastic composites. So let's not waste any more time and get into it. So first thing first is I have this picture here from the company Orthotropic Engineering. And on this graph, what you can see is to the left of the tensile strength property. So you take a fiber and you pull it. So that's the tensile strength. And on the bottom axis, you can see the tensile modulus. So that's pretty much the Young modulus, the stiffness of the material. And what you can see on top is you have the IM, HS, and HM carbon fibers. So generally speaking, you will see the IM carbon fiber being used in aerospace type of applications because it's got great tensile properties. The HM will be mostly used, say, in high stiffness applications, but it comes at a cost, which is the tensile properties are not as good. You can see the carbon fibers are on the upper end of performance, but you can also see S-glass and E-glass. And what these are is the two different types of glass fibers that's available out there. So S-glass is the premium, expensive version, and the E-glass is the cheaper version that you can see being used in so many applications. And in between, you have Kevlar, and at the bottom, you have flax, which is a natural fiber. So today, what I'm going to be doing is I'm going to be going through all of these fibers. And the intent is I want to show you how do these fibers interact with thermoplastic composites. It's very specific to thermoplastics in this video. So let's go straight into carbon and glass. So carbon and glass is used across so many industries, and that's why these are the materials that are the most commonly used across thermosets and thermoplastics. So to the left, we've got carbon, which is very good in stiffness properties, but it is also a very expensive material. So it tends to be used mostly in, say, motorsports or maybe aerospace. And to the right, we've got glass. Glass has got incredible toughness and impact performance, and it's used as a material such as in fillers or continuous fibers in automotive and in general use and so on. Both of these material types are used extensively across industry, and there's very good reason for it. We've been using these materials for a long time. We understand how do they perform, and therefore they're used in so many applications. Now, this also means that there's a lot of thermoplastic options when it comes to carbon and glass fiber. If we go into the next one, I thought I'd talk a bit about natural fibers. So natural fibers is gaining a lot of popularity lately, and you can see it being used in injection molding compounds. So in the top left, you can see a material which has been injection molded with natural fibers as a filler there. And historically, we've been using mostly glass fibers as fillers, and glass fibers will improve the properties of your injection molding, but will also damage your tool over the long run. So generally speaking, you have lower tool life. Recently, there's been a lot of companies using natural fibers. This has got sustainability reasons for it, but also the natural fibers can be reasonably cheap and therefore gets used in applications which are not ultra crucial. So for context, as you've seen in the earlier chart, natural fibers are lower than the cheap version of glass fiber, but you still have certain applications where they get used. So what we have at the bottom on this chart is a panel which has been formed by the company Lanxess. And what they did was they took a continuous fiber panel, heated up, and then they formed it. And you can see the drapability of this material is quite incredible. So this is a really great demonstrator of what their material can do there. And the reason why so many people are interested in using natural fibers is, let's look at the global warming potential metric that was put together in this case by the company BComp. So you can see carbon fiber is orders of a magnitude more in terms of CO2 emission compared to, say, glass fiber. And whereas when you compare flax fiber in this case, which is a natural fiber made from the tree flax, and then you simply remove and you dry the fibers. So the CO2 actually is negative. So this doesn't release CO2. This actually takes CO2 from the atmosphere, goes into the fibers, and then gets turned into product. So let me tell you a bit more about natural fibers. So people have been looking at natural fibers for quite a while. And originally people were looking at natural fibers and they were encasing them in thermosets such as epoxies. So you have these beautiful looking panels, but in reality, these panels are now encased in a material that cannot be recycled. And really, you haven't really done much in terms of sustainability. And the reduction in CO2 emission is marginal when you include the epoxy resin and then you include everything else, unless it is a bio-based type of resin. So if I bring you back onto thermoplastic, one of the reasons for using these materials is thermoplastics, you can use a bio-based material. So I have a picture here from Black Fabric, and they're using a bio-based resin, in this case, a polyamide. There's a couple of them in market right now. So you have, say, PA11, which is made from castor oil. So there are a couple of bio-based resins which are existing out there. And the idea behind that is you will have a material which the fiber is carbon negative and the matrix can also be carbon negative, or at least very carbon low. One of the key components in using natural fibers with thermoplastics is you can't go too high temperature. Anything above 215 degrees, you're starting to degrade these natural fibers. So that's why generally these fibers are used with, say, PLA, which is made from corn, polyethylene or polypropylene, which is made from oil, and also you have a bunch of polyamide, which are lower temperatures. So I wanted to show you how the material can be made. And I have this video here from the Fraunhofer Institute. And as you can see, the material starts in as a standard kind of like dry fiber format. And what the Institute here has demonstrated is the material is realigned. So you'll see in a second. So let me pause on this. So you have a material which is oriented in a unidirectional fashion, and then it goes and gets laminated between two thermoplastic films. And that laminate gets fed into a hot roller, heated and melted, and coming out of the other end, you can see an impregnated natural fiber. It is a natural fiber which is encased in a thermoplastic resin. I was debating whether to include Aramid fibers here. So Aramid fibers are also more commonly known as Kevlar. Kevlar is just the brand name of an Aramid fiber. In this case, it's a brand name from the company DuPont because they invented it. And you can see that generally speaking, Kevlar has got incredible properties. As you probably know, Kevlar is used in, say, ballistic applications. And we haven't seen a lot of Kevlar being used in thermoplastic composites. The main one that I can see is Markforged, the 3D printing company, will be using these materials. In this case, you can see one of their components where the yellow part is actually the Kevlar and the rest of it is a standard polyamide material. Now, Kevlar does degrade at fairly high temperatures, so anything above 350, especially 400 degrees, the material really starts to degrade. But mostly this material is used with polyamides because they're quite compatible, but there's also challenges in compatibility with thermoplastic. Thermoplastic fibers, and you're probably wondering, thermoplastic fibers? So in this case, this is a thermoplastic composite. So I said that twice. And let me explain. I've got this screenshot here from DIT Weaving. So DIT Weaving is a company that makes a product called Pure. And Pure is actually a polypropylene fiber. So we have this drawing here, and let me explain what these are. So you have polymer B, which is a fiber. So this is a polypropylene fiber, which is encased, in this case, with polymer A, which is another polypropylene film. So it's a polypropylene fiber with a polypropylene film. Now, there's a difference between these two materials where the polypropylene fiber is a higher melting point than the matrix, the polypropylene film, so that you can melt the film, but leave the fiber in fiber form. On the market right now, there are two main types of fibers. So you have UHMW, so ultra high molecular weight polyethylene fibers, two brand names, Dyneema and Spectra. So these are made by American companies. And you also have polypropylene fibers, as we just saw, and a couple of brand names, Curve, Tegris, and Pure. Now, these fibers are generally speaking lower temperature type of material, and they tend to be used in ballistics. And that might explain why we haven't seen that much thermoplastic Kevlar type applications, because these are already very good options right now when it comes to ballistics applications, sports applications. So to the top, you can see a helmet which is made for demining. To the bottom, you can see a front splitter for a Ferrari, and at the bottom right is simply a manufacturing process from one of these companies making these materials. This type of material has been available since the early 2000s. So polypropylene or polyethylene fibers have been available, but the companies making them have been trying to get them, say, into consumer goods. They've been making luggages and they've been making winter sports protection type of applications, but they haven't really taken off. And now, given that thermoplastic composites are a material which is generally of interest, these fibers are also being looked at. Most of the interest at the moment tends to be the defense type of applications. I hope that today's video gave you quite a taster about the different types of fibers available out there and how would you mix and match it with the right thermoplastic. Because thermoplastics are processed at high temperature. What it means is some of the higher temperature thermoplastics might not be compatible with certain fibers, say natural fibers, because they will degrade it. So you have to be quite selective there. Hopefully you enjoy this video. Click the subscribe button and I will see you on the next video where I have quite a treat lined up for you, so you don't want to miss this out. Peace.